All right, everyone, welcome back. It is Wednesday, and today is our middle point for our analysis of light bulbs. Light bulbs. Actually, we're going to get into some more interesting material today, and we're going to start seeing the quantum mechanical aspects of light bulbs. And again, the purpose of all of this is a nice kind of warm-up to understanding quantum mechanics. The types of equations we're going to use today are very quantum mechanical in nature. They're a little bit easier, mathematically about the same, but a little bit easier to understand. Actually, when we get into quantum mechanics, most of the equations that we're going to be dealing with for the first month are going to be a lot easier. You're going to have less integrals that blow your head off for the first month, and then it changes anyway. But conceptually, why we're doing what we're doing is the hard part. Okay, anyway, that's next week. What are we doing this time? Okay, last time we talked about light bulbs. There's the light bulb. All right, it's really the Blackbody radiator. Black square box that's hot. But whatever, let's just call it a light bulb. The light bulb is L long. Just make it easy on ourselves, right? Okay, so what? First thing we did was to note that the spectrum of a light bulb looks like this, which is easy to measure, and we're going to analyze that. To analyze it, we first apply the Boltzmann equation, and one of the leaps we have to make is to understand that we're not going to be messing with wavelength like we messed with velocity in Maxwell-Boltzmann. Instead, we treat wavelength as a constant, and what we adjust is the number of photons for all the reasons that we talked about in the last hour. Okay, now with that, that means that although we're using energy, Boltzmann equation is of energy, we changed it to number of photons, just like we changed it to velocity for Maxwell-Boltzmann. Here we changed it to n, the number of photons. That allowed us to do the normalizer, and, that allowed us to understand the normalizer, which allowed us to calculate the average energy. Right. So, sorry, they're not the same thing. This is after doing the normalization and calculating the average energy of, for a particular wavelength of light. We usually put a little subscript like there to make sure you understand. That's the average energy for a particular wavelength of light, which is basically figuring out what the average number of photons will be, which basically is a balance between the wavelength of light and the temperature. The higher the temperature, the more average energy you get, the more photons will be coming out of this light bulb, which is perfectly sensible, right? That's why hot light bulbs are whiter. A really hot light bulb is blue, and a very cool light bulb is red. All right. Now, the problem is when I plot the energy as a function of wavelength, I see something that's shockingly different than the output of a light bulb, which automatically says to me something is very wrong about my understanding, and that sucks. So there's more to it. Okay, what's more to it? Let me go ahead. I'm actually going to jump ahead to the end of the lecture. Let me just tell you so you know where we're going. It turns out that this thing says that you can have any wavelength you want, right? Just plug in a lambda, and out comes whatever, which is what I graphed. Now think about this. The light bulb is yay big. It'd be like 2 centimeters, right? An average light bulb? Okay, so a 2 centimeter wavelength, a wavelength as long, as big as the light bulb itself fits just fine. But with that said, what about a longer wavelength? What about let's go crazy. What about a meter? What about a mile? What about a mile-long wavelength? What about a mile-long photon? Does that fit inside the light bulb? No. So what am I doing graphing, making this graph go higher and higher as I move to longer wavelengths? That's fine. It just doesn't work for a 1 centimeter light bulb. So you see, in terms of why the average energy keeps rising as you go to longer wavelengths, is that we're not taking into account that there's a finite wavelength of light that fits inside the box. So clearly that's going to take this graph at some point, it's going to drive it down, right? And so that's why the actual curve at some point goes down with increasing wavelength, and eventually goes to 0 because you can't have wavelengths bigger than the light bulb itself. Perfectly sensible. The only time anything perfectly sensible is going to happen in this class, so heads up on that. All right. Now, where it gets hard, which is what I'm going to spend Friday's lecture, is that while I think it's easy to understand, you can't have the number of the number of photons of wavelength larger than the light bulb is 0. This is really weird. The number of photons, the number of wavelengths shorter than the light bulb is more than 1. Right? So again, it's easy to understand why a mile long wavelength, the number of photons is 0. But when the wavelength is shorter than the light bulb, then you can actually have more than 1. And that's what we're going to spend all day Friday, understanding why that is. All right, now you may notice, okay, probably one of my better drawings of a photon. We have to start talking about photons. And I'm going to digital it, obviously, so that's what you're looking at right now. The main thing is to note that photons have an electric field and a magnetic field, and they're 90 degrees to each other. And they're oscillating in space. It looks like a sine wave. You want to remember that. It looks like a sine wave. And in this class, we're not going to really talk about the magnetic properties of light. The magnetic oomph of light is like 1,000th as strong as the electric component, the electric field component. So it's an electric field and a magnetic field. The magnetic field is weak. In this universe, magnetism is a relatively weak force. It is measurable. I mean, how do we know it's there? It's there, it's measurable, but it's hard to measure. For the most part, light's oomph comes from the electric field. So anyway, okay, so that's gone. All right, now that I'm talking about electric fields, you should know that I'm talking about Maxwell's equations. Maxwell's equations dictate how electric and magnetic stuff works. All right, so what about that? If you take Maxwell's equations and do some manipulation, what you find, there's 4 of them, right? Actually, Maxwell amalgamated the equations from other people, including Gauss's law and Ampere's law and all that. Anyway, if you combine 2 of them, what you find is you get something like this in 1 dimension. You get the double derivative of the electric field is equal to 1 over the speed of light squared, double derivative with respect to time of the electric field. Now, E is electric field, it's not energy. Unfortunately, there's only so many letters in the alphabet. So, God, right, energy, electric field, you're just going to have to keep it straight. There's no way around this. Notice I put a little vector, and that's because of the way I drew the photon. There's no way I'm going to remember to do that, so I might as well just go ahead and drop it. I'm just not going to remember to put that little vector hat on top of it. So please recall that I'm talking about the electric field of light. Some kind of description, mathematical function for the electric field of light. It would clearly, in this case, be a function of x and t, because how else could I possibly be taking the derivative of it unless it had an x and t in it, right? Okay, so there you go. Let's see, what do I want to tell you? That is a simplification. Again, this comes from manipulation of Maxwell's equations for electromagnetism. We have to start thinking, just like Maxwell Boltzmann, God, I keep saying that over and over again, we have to live in 3 dimensions. All right? So reality is, let me write this out a little bit more mathematically. The way that this works is we're going to do x and y. Yeah, I'm going to write the e. I'm like factoring it out because you know why? I don't want to have to write it 3 times, and that's seriously why I just did this. Of course, the function will be a function of x, y, and z, and t, yt, because I've got still the same thing is still on the right side. And it's still a function of x, y, z, and t. There we go. Okay. So this is our job, is to solve this. Now I'm going to take two approaches, and that will bring us to the end of lecture. And what I'm going to do is, first I'm going to come up with a sensible description for a function that is the electric field is this function. That is going to be the first thing I'm going to do. And then we're going to talk about using it to solve this, which is a differential equation. Now, I know that you are not required to take diffie-q, yet here we are. Actually, everything in quantum is a diffie-q. Everything is a differential equation. So I'm going to be covering differential equations. I know you haven't had it. And I know it's like, well, then you can't talk about it. No, I can talk about it. I just have to go over it, which is what I'm doing right now. But just understand, I am aware that you have not had it. I know that it's not required, but that's why I'm doing this right now, so that you can follow along. If we didn't use diffie-q, there really would be no class. You may be thinking, yeah, no class. Well, guess what? Your competition for those future jobs, they've had it. And that means that their record, if you don't have it too, their record's better than yours. And if they're from like Harvard, Caltech, MIT, UC, they've already got an advantage. You don't want to give them another one, do you? Because that'll be it. So anyway, so we're covering diffie-q. All right. Now, let me talk about the function first. As I alluded to before, is there a... I just noticed that there is a screen. Give me 1 second. All right, everyone, sorry about that. It took me 10 minutes to get rid of that thing. I didn't even notice it was there. Okay, so what am I talking about? I am talking about coming up with a function for the electric field. And as I alluded to before, definitely I think I'm going to stick with the sine, right? Obviously this is like a sine. I guess I could use cosine, but I'll pick sine. All right, so, and you'll see why in a second here. What we're going to do to develop this electric field function, which again will be a sine, I'll just go ahead and tell you that, is we've got to figure out the innards of the function. Sine of what? Again, we're just going to go with sine, but sine of x or y, shouldn't, maybe 2 pi x. That's what we're trying to figure out, what's inside of the sine. Now, we're going to figure out what wavelengths fit inside the light bulb, which is 0 to L bit. All right, so now what we're going to do is sensibly figure out what the wavelengths are, and then come up with an empirical equation for said wavelength. All right, it'll make more sense here in a minute, but let me methodically go through the allowed wavelengths. The reason I'm stammering right now is that the first one is weird. The first allowed wavelength is technically no wavelength at all. It turns out that, you can think of it this way. The light bulb could be cold, right? In which case there's no light in it at all, right? Now, notice that the way I've drawn the function is just to say it's flat at 0. Now, in terms of a sine function, you could do that by saying the wavelength is infinity. And so let's figure out what this wavelength is. So I know this one is weird. The rest of them make sense. But the light bulb may not have light. So I need to represent that. And I represent that with a flat line. Because I have to work with a sine function, I've got to contort that to fit. Okay, the way I do that is I'm going to say that the wavelength is 2L over 0, which of course is infinity. Okay, so again, I know that one's weird because now let me just go ahead and do one that makes a bit more sense. Okay, again, I'm talking about, when I'm saying 0 to L, I'm talking about the light bulb itself. This is what fits inside the light bulb, right? So right there. Okay, now this one makes a little bit more sense. It's a little funky, but it does make more sense, right? So let's do this. Okay, technically a half wave with a lambda of 2L over 1. Now the reason I'm writing this 2L is that I'm going to be able, I already know what my empirical equation is for the allowed wavelengths, and it's going to be a function of 2L. That's why I keep writing 2L. Anyway, now I'm asking you what's the wavelength of light for this half wave, and you may be thinking L over 2. No, it's 2L, right? A wavelength is a full cycle. That's a half cycle. I have to go out to 2L to see the full cycle. The wavelength is 2L. So that's why the wavelength is 2L over 1. And so, therefore, lambda over 2 is what the length is. Okay, now I'll do one more because, again, I hope, now I'll do two more, so that we can see what our empirical equation is. Obviously, the next candidate that fits, and you see what I'm doing is I'm having to have nodes at the beginning and end. If that, maybe that wasn't clear, but I'm hopefully making it clear right now. For the wave to fit inside the 1 over L, the 0 to L box, it's got to have nodes at the left and right. Okay, now what is this wavelength? It's L, or 2L over 2, and therefore the wavelength and the length of the light bulb are the same. And I'll do one more, which again, I think you see how you play this game. This will be a fully even. The lambda is actually it's right here. The full wavelength is less than the length of the light bulb. It's actually 2/3 L, and therefore 3/2 the wavelength is equal to the length of the light bulb. Okay. Now again, all of this is, other than this one, which is a little weird, I hope all of this is sensible. And notice that I'm able to derive a simple relationship between the length of how big the light bulb is and the wavelengths that fit inside of it. Now again, I wrote 2L because I happen to know that there's an easy way to do this. Is just to write the wavelengths are 2L over N, where N is 0, 1, 2, 3. See that? All right, so I made it easy on myself. And now I can know what all the wavelengths are that fit inside the box. Now I mentioned to you that I'm here to derive a function for this thing. So let's just worry about the x direction. Remember that the electric, oh, there's the little hat. The electric field will be a function of x, y, z, and t, but let's just do x right now, because why wouldn't I? Okay, so, and again, for obvious reasons, it's a wave, so it's sine. And let me point out that every wave can be written like 2 pi x over its wavelength. Now the reason that is that when you've traveled from 0 to a wavelength, your sine has gone a full cycle, which you know from trig in 9th grade is 0 to pi. Once again, a wave, to go a wavelength, means that the sine has to start out in 0 to 0 and end up at 2 pi. That means x goes from 0 to its wavelength. Right? So that's perfectly sensible. Now you can see why I did this, because now I can put this, I can describe this as a function of the length of the box. 2 pi x over lambda, which is 2L times n. And let me clean that up. That is sine n pi x over L. Now, I know that I'm going to have an x, y, and z, so tell you what, let me backtrack a little bit on my terminology, and let me write this n as nx. You know why? Because I'm going to have an ny and an nz. What I just did for x, I can also do for y and z, because of course I can. Let's see here. Yeah, okay, that was for x. Let me do y and z. Let me actually just write out the entire equation for the electric field of light. And what we're going to have, of course, is sine. Maybe I ought to speed up time here. No, I don't think I need to. I'm going to leave a little space here. Am I going to multiply or add them? I'm not sure. I'll have to talk about that. I'm going to talk about that next. For now, I'll leave a little space. So I want to point out to you that you probably want to multiply it, and that would be a good idea. That's actually the answer. I shouldn't be telling you that, but you could actually multiply them. Add them, sorry. Ugh. You could add them, but I'm going to leave that nebulous by just kind of leaving them alone. Okay, now for the t function, you're going to do that on your homework. But let me just go ahead and give you the, let me just show you what it looks like. I got to remind myself, 2 pi c times t, which is speed times time, over wavelength, right? Yeah. Okay, so that's the that's the t one. Okay. All right. Again, you're getting more used to equations that just go on and on and on, right? Now, the question is, do you multiply or add? Which is it? Do you multiply or add? Now, I'll go ahead and tell you that you multiply them. And now I'm going to explain why. And this is kind of Donko Nutso. This is the part where we're going to have to spend a little time understanding differential equations. Now, I know I just said at length that I know that you haven't had differential equations, so I'm covering them. I'm covering them. And this is an aspect of differential equations that will come up over and over again. Now, there's another thing that, as I've already mentioned, all of quantum mechanics, every problem is a differential equation. I will show you some diffie-q as though we were in diffie-q class in one of the extra hours. I'll show you how to solve a real diffie-q. But what I'm going to do for the class, which is actually what you saw me do here, is I'm just going to give you the answer. And right, because you haven't had it. And then what we're going to do is prove that it works, which is what I'm going to end today with. Now, before so again, I'm kind of giving you the end result. But let's talk a little bit about how diffie-q works, right? Differential equations. Okay, now let's just do x and t, right? Let's forget y and z right now. It's good enough to do x and t. Okay, now if we were in diffie-q class, here's the kind of thing that happens. Okay, so you know that, plus y and z, let's just forget that. Let's do this. Let's write this diffie-q. And actually, let me change it a little bit. Let me subtract that and equal 0. All right, a couple of things. For one, you saw me take the right-hand side and bring it over. You notice that I have not written the electric field function. The reason that I've written it the way that I have is that if we were in diffie-q class right now, this would be like a test question, and the question, the answer is what's the solution to this? So again, you're at a diffie-q class, and you see this, and like that's the question. Now write down the answer. You are probably asking like, what the heck am I supposed to do with this, right? Okay, that's double derivative. My bad. I understand that those are double derivatives, but what about them? Where is there a problem, right? I can see a double derivative, but double derivative of what? That's actually the trick to this. The what is the solution to the problem, which is our electric fields. I just had it up there a little while ago. Okay, so what you're doing when you see a diffie-q, and you're in diffie-q class and you're supposed to answer, and you're like, well, what the hell am I supposed to answer? What you're looking for is the function that satisfies that differential equation. You're looking for the function that the double derivative with respect to x minus the double derivative with respect to t times a constant is equal to 0. The finding of that function is the problem, okay? And that's our problem because here we are. Again, I'll give you the answer. In fact, I did. It's a sine function. But let's say, tell you what, to get you calibrated, what if the electric field was this? Now, I have double derivatives, so I'm going to want to have a square function. And there has to be an x and a t, right? Because I'm doing the double derivative with respect to x and t. So let me write this down, because it seems like this would be a good solution to this problem. Now, as for how you actually do the bloody mathematics to answer these types of questions, I will show you one example in the extra hour like a month from now. For now, let me just show you what doesn't work, and then I'll show you what does, and that's good enough. All right. Now, here we have this guy. And you should know enough to know calc to know that the first term, the t squared, comes out, and I've got the double derivative up with respect to x squared. Then I've got, tell you what, let's get rid of the 1 over c squared. Sorry to do that to you. I want to decomplicate it for this example. Okay, the double derivative of t squared allows the x squared to just pass through because x is not t, and that's why that happened over here. Okay, what is the double derivative of x squared? Hopefully you know the first derivative is 2x, the second derivative is 2. So this ends up being 2t squared minus 2x squared, which is equal to 0. No, it's not 0. 2t squared minus 2x squared, if t is not x, which it is not, does not equal 0. You may be then thinking, well, what the heck am I doing? I am showing you an example of what doesn't work. This is not a solution to this equation. So if you're in DiffyQ and you get this question, and that's your answer, you have failed the exam. That's what you do in DiffyQ. Not fail it, hopefully you write down the right answer, which here, in our more simplified, we're going to get that C. Let's do sine of x. Let's make it a little bit harder, kx, right? And sine of kt. Make it a little bit more interesting. All right, now when you do that, what do you get? All right, the first term, the sine of kt passes, and you get the double derivative of sine kx. And I think you know what that is. I hope you know what that is. That would be k squared minus sine kx. The double derivative of sine kx is minus k squared sine kx. You should know that. All right. The next term, minus sine kx passes through the double derivative with respect to t. The double derivative with respect to t is going to do exactly what it did before. Again, I know that I'm not showing you every step because I think you should be able to do derivatives of sine. You should be able to do that. And is this equal to 0? Other than I've permuted the sine, x and t. Yes, this actually works, right? This is that minus plus 0. So this is a valid solution. So this is what DiffyQ is. Now, let me point out one other thing. This is real subtle, but this is really important. This is something you've got to understand and know. Look what happens if I divide by the original function. Kt, kx. Right? So I'm dividing by the original function. Doesn't matter which order I put them in. 0, and you divide that by the original. I'm not going to skip this, right? Even though 0 divided by sine kx kt is still 0. Okay. What do you get? You get minus k squared plus k squared equal to 0 over sine blah, 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 which is 0. Is this correct? Of course it is. Look at it. Minus k squared plus k squared is 0. All right, well, you may be thinking, well, sure, but so what? There's a subtlety here, but it's terribly important. Each one of these terms is a constant, right? You saw how I could apply the solution, do some manipulation, and show that each term is in fact a constant. Now, that actually makes sense, right? K is a constant. Sine k, x is the thing that changes. K is a constant. So I could whittle this thing down into a statement of this constant minus that constant. Now, that actually makes sense. Now, let me point this out. Derivatives are like, what's changing about this function? This is asking what's changing with the electric field in terms of position, and this is asking What changes with the electric field as a function of time? When you subtract the two questions, you get a constant, 0. Now, 0 is not a very interesting constant, but it is a constant. Now, let me ask you this. How could this be anything other than a constant? Because if it's not, if it's a function, so if this is like sine x minus sine t, how could that ever be 0? How could the change in a direction be matched by a change in time such that those changes were in phase and canceled each other out? How does space and time speak to each other? Or how would x and y speak to each other such that if there's a little fluctuation in x, there's a fluctuation in y at the same time that cancels it out? How could it even cancel it out when they're in different directions? And let's even forget about how that happens over time. The answer is that doesn't make sense. You can't have these be functions, because how could one function cancel out another one completely so that the result is 0 when these are like different dimensions? It can't. But there is a solution, which is the one I just showed, when in fact these double derivatives are in fact constants in their own right. Now, two constants can subtract each other to get 0. That's exactly what I just showed you. That does work. Okay, so again, when we have these types of diffie-qs, each term is like a miniature diffie-q. Each one of these is a constant and can be solved in its own right. Now here's another consequence, and I'm going to save this for a problem set. You're going to prove this. It's going to be a while. But when you solve each like miniature diffie-q, what you get is a function of x, a function of x. Now, in terms of plus or minus or multiply a function of t, it turns out that what I just described only works if they're multiplied. So, big picture, when you have differential stuff equals 0, each one is a constant, and I've just shown you that. And in a problem set later, each function is its own, each x, y, z, t is its own function, and the total solution, you just multiply those individual functions. Again, that you will explore on a problem set about 2 or 3 weeks from now. So, going back to this guy, we've already figured out what each individual, we figured out what x was, sine x, blah, blah. Obviously, y and z will come out the same. You multiply them, you'll figure out that part. The t part is also on a problem set. It's very, very simple. Let me just give you the answer. Speed of light times time is what? Is that time? Is it distance? Divided by distance? The question is, why does this make sense? And I think I just basically gave you the answer. Anyway. Okay, with this thing, now that you have the solution, what you do is you're going to plug that into the original Maxwell equation thing that I mentioned at the beginning. Here, I'll just write this. I'm gonna take this over right here. Let me write out the original diffie-q problem, which is double derivative of x, which we know is some kind of constant, double derivative of y, times the electric field. Again, that's the electric field is a function of x, y, and z. I'm not going to write all that out. Equal to 1 over c. C squared, double derivative with respect to t. And again, the electric field is right up there. I think you can see that in the camera. Okay. So what? I will not go through the entire derivation because it's just rather tedious. You should be able to take the double derivative of a sine function, right? You should be able to do that. Let me just cut to the chase. I'm going to apply this thing to these equations, and then I'm going to simplify it, and I'll leave that to you to do that because, again, it really isn't that bad. But what you get is the double derivatives take the innards out of the equations twice, and there's also a minus sign. The double derivative of sine is minus sine. So there's the minus. The innards have pi and L, so I'm going to have a pi squared L squared that can be factored out of the nx squared plus the y term is going to give me a minus pi squared L squared and y squared. Again, I've factored it all. Okay. Again, just like I said, I'm ending up with a bunch of constants, and on the other side is going to be a minus 4 pi squared. You know what? That time one is going to bring out a c squared, which is going to be divided out by that c squared. So I'm going to end up with a 4 pi squared over lambda squared. Make sure you can see that. There we go. Okay, again, I'm hoping you know enough calc to be able to do those double derivatives and then divide out all the signs, just like I did in that example, and you get this. Okay, let's just get rid of those minus signs. Again, I'm writing over my own equation, sorry about that. The last bit is to notice that this looks just like a vector. X squared plus y squared plus z squared is what? It's like a radius squared, but when it's nx and ny and nz, we'll just call it n squared. So it's like a net length. Okay, so here's what you get out of that. Pi squared n squared divided by L squared is 4 pi squared over lambda squared, where n, of course, n squared is an x squared plus ny. Now, one thing to remember about these nx, ny, and nz, these have to do with the number of nodes, basically, of the light inside the light bulb. Remember our previous example? As any one of these n's gets higher, the wavelengths get shorter and shorter because the number of nodes technically increases. So just remember that as nx or ny and nz, as they increase, the wavelengths of light get a bit shorter. I should have pointed that out before, sorry about that. Of course, what you can then do is simplify this, and I'll stop here. Lambda squared is 4L squared over n squared. Now, what we've done with this is we have now a relationship for every wavelength of light that fits inside of the light bulb. We have a relationship that tells us what every possible wavelength is. The only thing that's slightly complicated is that we have this number, which, as you recall, was related to the wavelength of light so long as the light started and stopped inside of the light bulb. And again, I was remiss, I should have pointed out that you can actually look at the number of times that the wave crosses the origin, right, which is a node. You can basically say that in each one of these nx and ny and nz's is the number of nodes. And that's about it. So last bit, what we're going to do is, now that we see how there are certain waves that fit inside the box, what we're going to cover next time is that, again, only certain waves are allowed, but get this. As you go to shorter and shorter wavelengths, you actually have degeneracies kick in. And so it just gets higher and higher and higher. You actually have degeneracies kick in. If you have shorter waves, more of them fit inside of the light bulb. Now, when you multiply that by our previous calculation of the average energy, what you're going to get is something that is a perfect representation of the intensity of a light bulb as a function of wavelength, which is what we're really trying to do. The only problem is that I need to know how to calculate the number of ways that these wavelengths fit inside the light bulb. In other words, these little sticks that I'm just like filling with photons, these like little posts, imagine these are like little posts and I'm filling them with like little rings. I'll do a little graphic on that. Maybe I'm doing that right now. That is a mathematical feat that we're going to do next time. All right, I will see you all then.